All right, so I said we're going to jump into new stuff, but I'm actually going to do one more video of a review here because we talked about the binomial probability distribution, and you can see that down here. And I just want to review that because repetition is the mother of mastery, and the more you practice, the more you progress. So here's the general binomial, and here formula and binomial probability formula. You could say it both ways, apparently, according to ChatGPT. And so we're going to review that and review this here. You can pause the video and you can take a read through it just to review it. Repetition's the master of mothering. Practice leads to progress. And then we also have this terminology, right? We have an experiment which produces an outcome. And that outcome, all of the possible outcomes are a sample space. And so the outcome could be one of the things in the sample space, right? One of the possible outcomes, one of the possible sample points. That's the phrase I'm looking for. The outcome can be one of the possible sample points in the sample space. And then an event is a subset of the sample space. And the event, we can measure the event of the probability of the event, right? We can measure the probability of the event of getting all heads, and some combination in two tosses. And so that's that terminology there. And so here we have the variable, and randomly it could be one of these values here. And we take that variable and put it into a function. That function or that formula, you could use those words interchangeably, is going to produce the probability of that. And now what word do I want to use here? That event, right? The event is going to be some sample point or collection of sample points, which is a subset of the sample space, right? And an outcome also will be the outcome, right, of an experiment. So if we do an experiment, we get the outcome. It'll be some sample point, and the sample point will be, right, one of these things here. So that terminology still kind of comes to me. I don't totally have it. But we've got an experiment which produces an outcome. An outcome is one of the sample points in the sample space. And then an event is something we can measure the probability of. An event is a subset of the sample space. And that subset could be one sample point, or it could be multiple sample points, or it could be all of the sample points. And so here we have a variable and we pass that into a function. And if we have that outcome, we get that sample point here. Or if we're measuring the probability of a sample point, right? What's the probability of a sample point? We can say that event, right? When this event occurs, when we sell 2 cars, the probability of that is 0.24. But the point of this is you could take the variable, you could put it into a function, you could get the probability of that event occurring, that sample point, which is a subset of the sample space. You could get the probability of that event occurring. And being careful just to make sure I use the right words. And when you have this framework, right, like take the variable, put it in a function, get the probability of that event occurring, then you could extend that, and you could go into things like the binomial formula or the binomial probability formula. And binomial, I think nomial, kind of a number, by kind of 2. And so if we look here at what this is, we're going to review this. Understanding discrete probability distributions. Discrete probability distribution is a statistical tool that describes how the probabilities are distributed over the values of a discrete random variable. And in other words, it tells us the likelihood of each possible outcome for a random variable that can only take on distinct separate values like integers. So the likelihood of each possible outcome of a random variable, how many cars are sold each day, they can only take on distinct separate values like integers. Connection to random variables. Random variable in statistics is a variable that takes on different values determined by the outcome of a random phenomena, flipping a coin, how many customers come in and buy cars that day. When this random variable is discrete, it means it can take on a specific set of distinct values, number of heads in 3 coin tosses, number of cars sold, etc. A discrete probability distribution provides a way to map these distinct values to the respective probabilities, right? So that's what this is, mapping the distinct values to the respective probabilities. I don't know why. It's just learning the language, man. Donut with sprinkles in Chinese. How do you say it? This mapping shows how likely each outcome is when an experiment is repeated many times. Components of discrete probability distribution, right? So we have the random variable, then we have the probability. Here's the probability function. How to represent discrete probability distribution. Which event is going to occur, what is the sample point that we want to know the probability for out of the sample space, And then here is the probability for this variable, this event occurring, that sample point being an outcome. And the probability of all those has to add up to 1. And then they give us an example of rolling a die, 6 sides. So the probability of each of the values 1 through 6 is 1 over 6. And then that's a summary of it. You can pause the video and you can read it. And then we asked, right? I asked, how did you calculate the probabilities here? Is there some formula to determine this? And this is the probabilities of 0.25, 0.5, and 0.25 for flipping a coin. And random variable alongside discrete probability distribution represented in 3 ways. So I'm just looking for, X is the number of heads when flipping a coin twice, right? Number of heads when flipping a coin twice. We asked, how did you calculate that? And so then they gave us this kind of like logical way to think about it. Identify the random variable, represents the number of heads. X can be 0 or 1 or 2. So in 2 flips, you could get 0 heads, 1 head, or 2 heads. When flipping a coin twice, each flip has 2 outcomes, heads or tails. So the total number of outcomes for 2 flips is 2 times 2 is equal to 4. And that's kind of like if you think about the tree diagram. You've got the first step is 2, and then the next step is 2. So you can get heads or tails, and you can get heads or tails off that, or you could get heads or tails off of that. And so you could have heads, heads. If you follow those branches on the tree down, 2 steps, and each step has 2 possibilities. You could get heads, tails. You could get tails, heads. You could get tails, tails as the 2 flips. That's the outcome, 2 heads. And so here, the probability of no heads would be, there's 1 outcome. So 1 out of 4. The probability of 2 heads, there are, the probability 1 head, and 1 head, the probability of 1 head is these 2 right here. So you got 1 head, there's 2 outcomes, and the probability of 2 heads is right here. And the probability of 2 tails, sorry, so that's no heads, 2 tails is right here. And so that's 1 out of 4, this is 2 out of 4, this is 1 out of 4. And so that's where you see those calculated. And then there's a formula for calculating that, which is the general binomial formula. And this is a kind of cool thing to see because you have a variable, you put it into a function, and you get the probability of that event, right? That event occurring randomly. And so here, for binomial distribution, bi being 2 and nomial, I'm thinking nomial kind of means like name to me, but also I guess maybe it could be number. Right? You could determine, right, for a binomial distribution, the probability of getting exactly k successes. So here's k successes. And n independent trials, here's n independent trials, is given by this. And so if we want k successes, 0 success, 0 heads, 1 head, 2 heads, and 2 independent trials, 2, 2, 2, we just do that formula there where p is the probability of success on a single trial. So that'd be 0.5, 1 minus 0.5, and then n minus k is going to be 2 minus whatever this is, the k. And so here you have 2 minus 0 and 2 minus 1 and 2 minus 2. And anything to the power of 0 is 1. And so then we calculate those probabilities using the binomial formula. And so to use the binomial formula, binomial probability formula, you can pause the video and you can read this. But to use it, you have to have a fixed number of trials, n. You have to have 2 possible outcomes per trial, right? Success or failure. You have to have a constant probability of success. From trial to trial, it doesn't change. You flip the coin, it's always 50-50, heads or tails. And the independent trials, so the outcome of one trial can't influence the other. So when you have all those situations, you can calculate the probability of, how many successes, getting heads, where k is number of successes out of how many trials, n. You could calculate the probability of that. The probability of getting 0 heads out of 2 trials, probability of getting 1 head out of 2 trials, probability of getting 2 heads out of 2 trials. You could calculate that probability. Why is this useful? Well, maybe you want to gamble. And in statistics, maybe we should call it how to gamble more effectively at Las Vegas. Like maybe more people would take that class if we called it that. And they might have more fun. So that's the binomial probability formula. And what that shows us is that we could take a variable, and here the variable that's being put in is what is the number of successes of getting heads. It's 0, 1, or 2. We could take a variable, 0, 1, or 2, in the flipping the coin thing, and we could put it into a function, and we could get the probability distribution. And it's discrete. It's a discrete probability because you can't get like a partial head. You can't get a partial tails, right? It's the whole deal. And so that's that shows us that, you know, once we have a variable, we could put it into a function and get the probability. And so here's the function. And once we have a variable, right, the variable here being 0, 1, or 2 heads in our flips, that's the number of successes out of how many trials we could get the probability. So it's a little bit of a review of the binomial probability formula or function, and it's also a little bit more of a review on discrete probability distributions. So I'm going to call this video Discrete Probability Distributions, and discrete probability distributions, and then the binomial probability function or formula. I don't know, either one of those two. See you in the next video.